reconstruction of ancestral genomes.
Thanks. So today I'm going to talk about preliminary work on this topic, selecting genomes for reconstruction of ancestral genomes. With many genomes has been completely sequenced, so ancestral genome reconstruction proposed. So one of which is to reconstruct genome of mammalian ancestors. So using this phylogeny. So so I participate in this project. So this motivates us to consider this problem. So you're giving a phylogeny P of a set of genomes, integer chi, reconstruction method T. Then to find k genomes in the phylogeny, that gives a highest accuracy of reconstruction the ancestor genome at the root using the method P. So there, which one? This one? Or which one is? There are two reasons for this. So the first one is obvious. So it is not always possible to sequence all the current genomes below ancestor. So another one is the more taxa do not necessarily give a highest reconstruction accuracy. So this is a little bit not obvious, so I will give the example. So this is an outline of the talk. So first of all, I introduce briefly the reconstruction accuracy. So because I give some examples about this observation. So more genomes are not necessarily better for reconstruction. So then I propose some greedy algorithms for the problems. So the part 2 is a joint work with Guoliang Li and Max Steele. So the part 3 is a joint work with Guoliang Li and Jian Ma. So there's different methods for reconstruction. So the parsimony probably is the oldest one. It's very popular. So basically, it ignores any probability changes along the branch. So it's easy to use. Also, it's very efficient. So also there are some complicated methods like the maximum likelihood method, also Bayesian method. For this reconstruction, we assume the tree is given. Okay, so here, we consider this problem with the Fitch method, also the maximum likelihood under the Jukes counter model. So this model is a simplest model. So the character involved by a symmetric reversible Markov process. Also, the substitution probability of any sort is the same on the branch. So also for the analysis simplicity, we assume there are only 2 states, but it works for all the multiple states. Since the model we consider is symmetric, so the reconstruction accuracy is independent of the prior distribution of the states into the root. So therefore, the reconstruction accuracy can be calculated in this formula. So the sum over all the state configurations, also called the leaf labelings. So the probability that the 0 involved into this state configuration, the I0 dk is an indicator function. So in other words, so the reconstruction accuracy is a sum of the generating probability of state configurations, which allow the true state 0 to be recovered by the method K. Okay, so this is how to calculate the reconstruction accuracy theoretically. So this is not the new problem. It has been studied for a number of years. So there are simulation study. There are also some theoretical study. So okay. But for the feature method, the reconstruction accuracy is defined slightly different, because it will sometimes the method give the ambiguous answer. So therefore, we define the accuracy in these ways. The first one is an ambiguous reconstruction accuracy, which one is very simple. So basically, it is defined as a probability the Fitch method output the true state is a root. Okay, so this is very simple. But also we consider the reconstruction accuracy in this way. So it's defined as the unambiguous reconstruction accuracy plus the half of the probability that the Fitch method output all the state into the root. So basically, in this way, so we can guess the answer if the output is all the state. So this is so in the history. So in the literature, these two probabilities are considered separately. But here we put this together. So since the feature algorithm works recursively from the root from the leaves to root, so therefore these three probability can be calculated recursively by a dynamic approach in a very efficient ways. So therefore, say we can do some symbol analysis. So this is the examples to show the reconstruction accuracy is not the monotone function. So basically, this is an unbalanced tree. There you will see there's a large clade there, but with a long stem. Also, they are very short single sister lineage. But this phylogeny is used if the fossil record also the current the data about current species are used for reconstruction, right? So this is for this one we can prove. You see the reconstruction accuracy of the parsimonial Fitch method is actually smaller than the P1, so which is the conservation probability on the short lineage, the system lineage. Here, so we use the conservation probability for the analysis. So the mutation probability is equals 1 minus the PI, something like that. So here we see by the method, so we consider this probability. The Fitch method output the true state into the root. So there are two by the method. So there are two possible ways to get the true state. The one is so because this is 0, that this leaf must have a state 0. That is in this one. So in this node, the method must output a true state or all the state. There are only these two possibilities. So therefore, this true probability can be calculated in this way. So this is the conservation probability on this lineage. Then this is the probability that the method output these two answers. Okay, since so the state can be changed or can stay same. So therefore, we consider the two conditions here. So in this way, we simplify this into this. So this is also this. So this is the probability the Fitch method gives the true state into the root. But similarly, so we can also calculate this probability. The Fitch method output all the states. So we put this together. So we have this symbol formula. So it equals the P1 plus half of the 1 minus P1 minus P2 times this probability the method gives the wrong answer. And this then plus half of P2 minus P1 times the probability the Fitch method gives the true state in this internal node Z. So therefore, if we assume this lineage is shorter than this one, then the conservation probability of P1 is bigger or equals P2. So therefore, this one is a negative term. This one also a negative term. So therefore, the reconstruction accuracy is smaller than P1. So this is observation about this reconstruction accuracy. So we know in general the maximum likelihood method are better than this parsimony method, because the maximum likelihood consider the changes along the branch. Okay. However, so the maximum likelihood cannot do better than this. So by the way, so if the trace is this kind of a particular the comb-shaped tree, then there's a formula to calculate the reconstruction accuracy in the limited case. So this is the numerical calculation of this reconstruction accuracy. So this is the conservation probability on each branch. Here we assume they're same on all the branch. Then this one, the green one, is the reconstruction accuracy. So this one is unambiguous reconstruction accuracy. So then back to the maximum likelihood method. So the method can do better, but it's not too good. So therefore, the reconstruction accuracy is equals P1 in this case. So therefore, this indicate for this kind of unbalanced tree, you see the information in this large clade are not used at all. So basically. So this is another example to show we use the false leaves to reconstruct the state in the root. It's better than use all the leaves. Okay, so this is only true for the parsimony method. So for the maximum likelihood, so the using all the leaves is a little bit better. So therefore, basically, it's so when the tree is not balanced, so this so observation occurs. So therefore, to see how often this happens, so we did some experiment analysis. We generate the random trees according to the U model, that we assign the conservation probability along each branch. So here, the conservation probability is the same on all the branches. Right? So this is the counting of the bad trees. So basically, you see when the conservation probability is smaller, than this occurs very often. When this conservation probability is higher, then this less occurs. So this is the detailed calculation about the accuracy. So we also did some simulation to compare these three methods. I don't know whether this report or not. So so basically, on all the trees we generate, seems the marginal maximal likelihood performs the best. So it outperforms all the other two methods. So on the 80% of the instance, the marginal maximal likelihood is straightly better than the joint maximal likelihood. So this kind. So this is the observation. So in the part 3, so basically I propose two methods for this problem. So this is the problem is quite simple. This problem is unlikely polynomial solvable, but no proof yet. So as a result, so we propose two greedy algorithms for the problem. So two natural ways to do this. The first way is a forward grading algorithm. So basically, we select the genomes one by one. So in each step, we select one genome which has the largest increment of the reconstruction accuracy. So we output. So another straight way, so is a backward selection. So basically, we just threw away the bad genomes one by one. So there's two different ways to do this. We tested the performance of these two ways. Then we find out the backward method is a little bit better than the forward method. Okay, so this is this is accuracy. That this is a number of the leaves we selected. So this is the total number of leaves in the tree is 16. This is for the marginal maximal accuracy. So the performance is quite similar. So this is the difference of the accuracy. So between the reconstruction use all the leaves and also the selected leaves using the method. Okay. So I think I'd like to conclude the talk by a few of remarks. So basically, we observe this factor. So the reconstruction accuracy is not a monotone function for the parsimony method. So this is another kind of inconsistency of the method. So therefore, there are several implications of this observation. The one is this. So probably you see the parsimony method, the maximal likelihood method, might not explore the full power of incorporating the fossil record into the current data. So therefore, if somebody study this kind of reconstruction problem, they may need to modify the method a little bit. So therefore, because of this one, if one is not careless, then you may have draw the wrong conclusions. So, so another third problem is a reconstruction accuracy function monotone in ultrametric phylogeny. So it seems true when the number of taxa is large. I mean, because when there are only 2 leaves, this is the unbalanced tree we considered. Okay, so this is technical. So this is the numerical calculation of the reconstruction accuracy for the complete binary tree in the limit limit case, more or less. So in this case, there are formula about this reconstruction accuracy. This is in the Max Dew's paper in 1989. So in this, when the conservation probability is smaller than this 7/8, then basically the reconstruction accuracy is equals 1/2. So it's the same as the conservation probability along the lineage, the limit case. So when the probability is bigger than 7/8, so the reconstruction accuracy is better. So in this case. So also, so we formulate the genome selection for reconstruction problem. We also give 2 greedy algorithms for this. I think that's all. Thanks.
I have one question.
Just to make the point clear, maximum likelihood is monotone, just not strictly monotone, right?
No, yes.
It is weakly monotone.
It's not sure, but for that case, it's still monotone.
No. There is something that's called the data processing lemma, and it says that maximum likelihood is monotone. It's weakly monotone. So if you add more data,
you mean it's a no result, right?
It's a non-result, yes.
Okay, so maybe I need the right phrase.
Okay.
Yeah.